Let's take a look at some additional properties of matrices. I'm going to write us out a 3 by 3 matrix here, and I'm going to end up with several different matrices here. So I'm going to call this one A. If you have a matrix and one of the rows is all zeros, it doesn't really matter what the other entries are, then the determinant of that matrix will be 0. If you think about it, knowing that you can take any row or any column and use that as your coefficients, use that to find your cofactors, that's going to be the sum of those terms is going to be 0, because you'll have 0 times a subdeterminant plus 0 times a subdeterminant plus 0 times a subdeterminant. If you have a matrix, I'll call this one B, and two of the rows are identical, then the determinant of that matrix will also be 0. And I hope that's fairly obvious too. If I do some row operations on this and I take row 1, multiply it by multiply it by -1, so -1 times row 1, and add it to row 2, and replace row 2 with that information, then I get, I'll call it B prime. It's a different matrix than B. Then I get 1, 2, 1. Row 3 doesn't change. But row 2 is now the opposite of row 1 plus row 2, which is, because they're identical, it's a row of zeros. So we're right back to where we started in the case where in matrix A, where we have a 0 row. The determinant is going to be 0. If you have a determinant, I'll call this one C, in which one of the rows is a scalar multiple of another row, then the determinant of that matrix will be 0. Well, again, this is just a case of, say, C prime. If I take -2 times row 1, add that to row 2, and put that in the row 2 position, if you will, then row 1 doesn't change, although I'll use it to do some computations. Row 3 doesn't change, but row 2 is now the opposite of 2 times row 1. That's going to be -2, -4, -2, added to row 2, which is 2, 4, 2, and so that's a 0 row also. And so I'm just using elementary row operations to indicate, to sort of demonstrate why each of these properties holds. And those properties again are, if you have a 0 row, the determinant will be 0. If two of your rows are identical, then you can add a multiple of one of those rows to the other to get a 0 row, so your determinant will be 0. If one of your rows is a scalar multiple of another row, then you can add a multiple of that row times the other to get a 0 row, and your determinant will be 0. So these are really all the same thing, but with a slightly different perspective, I guess you could call it. You may look at a matrix and say, oh, look, there are all zeros in that row, and you'll just know right away that the determinant is 0. This can produce, with one elementary row operation, this can produce a 0 row, but when you just look at it, it may not be obvious. As obvious as the case where there's already a row of all zeros. Because they're identical, though, you can say also that will, with one elementary row operation, that will produce a 0 row, which means you'll also have a determinant of 0. And the same thing is true when you have a scalar multiple. This is actually also a scalar multiple, right? This is really the same thing. Scalar multiple of this row is 1 times this row. So these are really the same thing. This is slightly different, I guess. This is a special case. And this is the one where you already have a 0 row. You don't have to go looking for it. So that is 3 of the 6 properties that I want to look at that deals with rows. There are three additional row properties that I think are useful here. And so I'm going to go to the next screen to talk about those. All right, for my other properties, I'm going to use some smaller matrices here just to demonstrate the property first, and then I'll tell you what it is. But know that like our previous video, these properties hold in the case of any n by n matrix, any square matrix. So let's take matrix A, we'll call it 1, 2, 2, negative 1. And matrix B, I'll call 0, 1, 1, negative 1. And I'm going to first do matrix multiplication on these two. So I'll get A, B. Here is A is 1, 2, 2, negative 1. B is 0, 1, 1, negative 1. And that result is 1 times 0 plus, I have to do this with my fingers. You can't see my fingers hovering over the screen here, but I have my left finger, my left index finger over the first 1, this 1 right here, and my right index finger over this 0. And then I'm going to move across and down. So I have 1 times 0 plus, move across and move down, 2 times 1. And that came from row 1 in my first matrix and column 1 in my second matrix, so it goes in the position of row 1, column 1 in my answer matrix. All right, now I'll do the same thing, but with row 1 and column 2. So I'm no longer looking at this column, I'm looking at this column, but I'm going to move starting in with my left index finger over the 1 in column in matrix 1. I'm going to move my finger across there and down over column 2 in matrix 2, in matrix B. So I get 1 times 1 plus 2 times negative 1. And that's my row 1 from column A, sorry, row 1 from matrix A and column 2 from matrix B. So it goes in the row 1, column 2 position in my result. All right, now I need to do the same thing for row 2 with column 1 and row 2 with column 2. So I'll just do that a little bit more quickly here. I get 2 times 0, which is 0, plus negative 1 times 1. So I have 0 plus negative 1. And then 2 times 1 is 2, plus negative 1 times negative 1 is positive 1. So my resulting matrix, the result of multiplying matrices A and B with A on the left is 2, negative 1, negative 1, 3. And now what I want to do is I want to look at the determinants of these three matrices. The determinant of A, the determinant of B, and I'm going to compare those to the determinant of AB. So the determinant of A is 1 times negative 1, which is negative 1, minus 2 times 2, which is 4. So negative 1 minus 4, that's negative 5. The determinant of B is 0 times negative 1, which is 0, minus 1 times 1, which is 1. So that determinant is negative 1. The determinant of my product is 2 times 3, which is 6, minus negative times a negative is a positive. Negative 1 times negative 1 is positive 1. The result is 5. Now, here's what's so cool about this. The determinant of the product is equal to the product of the determinants. So you don't actually need, if all you need is the determinant, you don't actually need to do the multiplication, the matrix multiplication. If you want the determinant of this matrix, all you need to do is find the determinants of these matrices and multiply them. You get the same thing. So that's that property. Here's another really interesting property. If I take a matrix, let's go with a nice, let's just use A again, the same A as we have up here, 1, 2, 2, negative 1. The transpose of that matrix, A transpose, is the matrix that you get by taking each row and turning it, oh, I'm going to get the same thing here, so that's not going to help me very much. Take each row and turn it into the row 1 becomes column 1. Row 2 becomes column 2. I get the same matrix, so of course the determinants here are going to be the same. So I'm going to erase this. That didn't work. And I'm going to use a different matrix. Let's try it with B. Now that won't work either because the diagonal, the upward diagonal is the same in the same way as it was here. So I'm going to get 0, 1 for my first row and 1, -1 for my second row. And that's what I have, so that's not going to work. So I'm going to have to pick a completely different matrix here. Let's try something like, oh, let's just go with 1, 2, 3, 4. The transpose of this matrix is 1, 3, 2, 4. Let's take the determinants of those. So the determinant of C is equal to 1 times 4 minus 2 times 3. And the determinant of C transpose is 1 times 4 minus 3 times 2, which is the same. Now, because of the things that we moved around, the result, the determinants are the same. Essentially, this diagonal doesn't change, right? And the result of the multiplication in the opposite direction is the same as well. It turns out that this is true even for a 3 by 3 or a 10 by 10 or a 100 by 100 matrix. As long as it's square, you can use this property as well. I'm going to stick with matrix C for this last one, the last of these. I've already figured out its determinant, so I'll just write it down. The determinant of C is -2. We found that up here. But now I'm going to do a little bit of matrix arithmetic. Put a dividing line here. I'm going to take 2C, which is the matrix 2, 4, 6, 8. Okay, and that is, the determinant of that is, write that differently, the determinant of the matrix 2C. Now that's a new matrix. I'm just retaining its name 2C. Instead of calling it D, for example, I'm just calling it 2C because that helps me know where it came from. It came from multiplying the matrix C by 2, which is scalar multiplication. The determinant of this matrix is 16 minus 24. 16 minus 24. That's 2 8s minus 4 8s is -2 8s, which is -16. Sorry, it's 3 8s. It's -8. 2 8s minus 3 8s is -1 8. So that's -8. And let's observe that that is just the determinant of the original matrix times 4, and I'm going to write it in this form, 2 to the 2. The reason I'm writing it in this form is because the only reason we got 4 in the first place is that this is a 2 by 2 matrix. Our n value is 4 here. We talk about n by n matrices. Okay, so there are two 2's going on here. One is this 2 right here that we use to multiply C by. And the other is from the dimension of the matrix, right? We have an n by n, which in this case is a 2 by 2 matrix. So our n value is 2, and that is this 2 right here. This 2 comes from multiplying C, the matrix C, by 2. The exponent of 2 comes from the dimension of the matrix. So, for example, I'm going to borrow some space above my previous, or within my previous example here. There. If I had matrix D, and I'll make it a fairly simple one, but I'm going to make it a 3 by 3. Let's go with 1, 1, 0, 0, 1, 0, 2, 1, 1. So there's my matrix D. Now let's find 2D. That means multiplying everything in the matrix D by 2. So I get 2, 2, 0, 0, 2, 0, 4, 2, 2. And I'm not going to work out what this determinant is. I will do this one. I'll find D's determinant off screen. I'll be right back. Okay, so it turns out that the determinant of this matrix is 1. The determinant of this matrix is 2 to the power of 3 times the determinant of the original matrix. That's going to be 8. And the point here is that this 2 comes from this 2 here. We're doubling the values of everything in the matrix D, and the 3 that you see in the exponent here comes from the dimension of the matrix. This is a 3 by 3 matrix. N equals 3. So 2 to the power of n, or k if you're multiplying by a value k to the power of n times the determinant of the original matrix. The second property we looked at on this screen, the one about transposing, this is a really interesting thing to have to look at, because what's happening here is I'm taking the rows of this matrix and turning them into the columns of this matrix. So I'm going to look at 3 more properties on the next screen, just very briefly, that reflect a couple of properties that we already know, but with a slightly different perspective. Okay, we're going to look at some things in review here so that we can use them to learn something new. A couple of videos ago, we looked at the idea that if I take a matrix A and I swap 2 of its rows, it's one of my elementary row operations, just reverse the order that 2 of those rows appear in, then when I take the determinant of A and I take the determinant of the new matrix, which I'm calling B, the determinant of B, the matrix I get by swapping those rows, will have the same numerical value as the determinant of A, but it will be the opposite sign. And if I take, say, a row in matrix A and multiply everything in that row by K, then replace row A with the new values, then when I take the determinant of the new matrix, it's going to be the same as K times the determinant of the original matrix. And lastly, if I add a scalar multiple of a row to another row, I add row B to some constant times row A, and make that my new row B, then the determinant of the matrix that results from this operation doesn't change from the determinant of the original matrix. I didn't point out in the previous video, on the previous screen, and I probably should have, that it's this property right here that gives us that the determinant of, let's just write it out this way, the determinant of K, some constant, times a matrix is equal to K to the power of n times the determinant of that matrix. And the reason for that is basically this property right here. If I take K times row 1 and make that my new row, new row 1, then I take K times row 2 and make that my new row 2, and so on, then I'm doing this. I'm taking K and multiplying everything in the matrix by that number. And so if for each time I do this here, I end up with K times the determinant of A. However many rows I have here, I'm going to have that K to that power. So that's where that rule comes from. That's a little bit of a side note there, but it's relevant, okay? So now the thing that I want to talk about now, though, is this property that says that the determinant, I'm going to write it here, the determinant of the transpose of a matrix is equal to the determinant of the original matrix. Now, a very interesting outcome of this property is that basically, since all you're doing when you transpose a matrix is changing all of its rows into columns, that means that we can do column operations on a matrix and we end up with the same result. So, for example, if I take matrix A to be 1, 2, 3, 4, then A transpose is equal to actually says that the determinant of the transpose will be the same as the determinant of the original matrix. But it turns out then that I can switch, sorry, wrong tool here. I can switch columns here and get the same result as if I had switched rows here. So if I reverse these 2 columns, then it's just like I reversed these 2 rows in matrix A. So I can also use column operations and get these properties. And I will use, let's see, green. I'm in a green mode. If I swap column A and column B in any matrix, or column A times a constant and replace that same column A, or if I multiply column A by a constant, add it to column B and replace column B with that, then I get these same results, right? So the matrix that I'm talking about in the white, the elementary row operations are written in white here. That's matrix A. The elementary column operations are sort of written in green. I guess I could have written them a little bit more carefully. Could have written them out separately. But basically, those hold true for this matrix. But the thing is, any matrix can be written as a transpose. Any square matrix can be written as a transpose of any other matrix. So that means that I can apply those column operations regardless whether I've taken the transpose of a matrix first or not. So very quickly, by way of example, if I have a matrix B equals, let's say, 2, 1, 0, 0, 1, 1, and 2, 0, 0, then that is a transpose matrix. It's the transpose of its transpose. In other words, B transpose is 2, 1, 0, 0, 1, 1, and 2, 0, 0, and B is what I get when I transpose B transpose, right? So B is a transpose matrix, which means that I can apply these properties here. If I want to take the determinant of B, I can do it by taking the determinant of the matrix, let's see here, 2, 0, 2, 0, 1, 0, and 1, 1, 0. And then, because all I've done here is swap two columns, because I'm working with a transpose matrix, and I'm going to get the same determinant as I would have got by taking the determinant of this matrix. I'll get the same determinant for B with the exception of the sign, right? It's this one here. It's this property here. All I've done is swap two columns, so the determinants just have different signs. And the same things then hold true for any matrix if you swap columns around until the matrix is in upper or lower triangular form. You can find the determinant just by multiplying the values in the diagonal. So all of those previous properties still hold true. And really the key here is to recognizing that any matrix, even this matrix right here, is the transpose of a matrix. As long as the matrix you're looking at is square, it has a transpose, and it is a transpose, or you can think of it as a transpose of some other matrix. Okay, so that's how we get away with talking about column operations, and these properties hold for column operations as well.